Welcome once again. Today again we are going to continue our discussion on solution to the quiz exercise problems of chapter 5 from book of Gallian's edition 8. In the last class, yesterday, we discussed the solution to the questions from 1 to 11. And then after 11 to question number 12 to question number 14, that is 2-3 questions, they are very much related with the oneness and on-to-ness, so that they are not so much relevant. Okay, if you find any difficulty in them, you can ask me. So, but thing is that they are not so much related with this. Okay. And the question number 15 is let n be a positive integer and n is odd. So they are considering that n is some positive integer, that is n belongs to z plus, and of course 0 is not included here, z plus excluding 0. Positive, it means if you are saying that positive, it means that 0 is not there anyway, or else we can say that a natural number. You can say that n belongs to the set of natural number. N is odd. If n is odd, is an n cycle, n odd, or an even permutation. So basically they are asking whether the permutation is even or whether permutation is odd. So that we need to answer. Okay. So they have given that n is some odd, n is positive integer. Okay. So in case if n is odd, and there is some cycle which is n cycle. Okay, and let suppose alpha is some cycle, and they are telling that this is n cycle. So let us assume that this cycle is written as 1, 2, 3, 4, 5, and dot up to n, where n is odd. Okay, where n is odd. Then obviously we can write alpha as 1 n minus 1 and 1 n minus 2, 1 n minus 3, and so on, 1 3 and 1 2. So how many and remember that n is odd by assumption, n is odd. Okay, so how many 2 cycles are there here? Could you tell me how many 2 cycles? Hello. How many 2 cycles are there? There exactly n minus 1 2 cycles. Okay, n minus 1 2 cycles are there. Okay, so n is odd, it means n minus, if we have n minus 2 cycles, so n minus 1 will be even. Okay, so this means that this would imply that alpha is even. Alpha is an even permutation. Okay, similarly, if we have some permutation beta, in other case, if n is even, so let n is even in this case, and beta equals to, beta is some n cycle, so 1 2 3 and up to n. Okay, in the same way we can write 1 n minus 1, 1 n minus 2 dot and 1 2. Okay, so there are how many 2 cycles? So there are, if you see, there are n minus 1 2 cycles. 2 cycles. Okay, so because n is even, so this would imply that beta is odd because n minus, if n is even, then n minus 1 is going to be odd. Okay. Next question. This is just like we have seen in so many cases that if we have been, suppose we have been given this kind of cycle, this is 3 cycles. So obviously we can write 1 minus 3 and 1 minus 2. So there are two cycles. Okay. So this permutation, suppose for example this alpha, and here n equals to 3. So they are n minus 2, n minus 1, that is 3 minus 1, that is equals to 2. Two cycles are there, and if there are two cycles in product, so therefore alpha is going to be even. Okay. So if the cycle is even, so if cycle is of odd order, then the permutation is going to be even. And if the cycle is of even order, then that particular permutation is going to be odd. So this was the conclusion of last question, question number 15. In case of question number 16, if alpha is even, what about alpha inverse? And if alpha is odd, then what about alpha inverse? So they want to know the nature about whether if alpha is known, then what we can say about alpha inverse. Okay. So we can take let alpha equals to alpha 1, alpha 2, and after suppose for example alpha n. Okay. So here alpha I are 2 cycles. Alpha I are 2 cycles. Okay. And n is in first case alpha is even, so number of 2 cycles should be even, and n is even. So they are talking about what about alpha inverse. So alpha inverse, how we can write alpha inverse? We can use what we say that a reversal law. Okay. So alpha 1, alpha 2, alpha n inverse of this one. Okay. So we can write alpha n inverse, alpha n minus 1 inverse, and alpha 2 inverse, alpha 1 inverse. Since
hello sir.
Yes.
गुड आफ्टरनून सर. सर क्लास सर हम लोग का थ्योरी ऑफ रियल फंक्शन का क्लास चल रहा था अभी जस्ट मतलब 2 मिनट पहले एंड हुआ है सर. अभी आप टोटल कितना क्वेश्चन करा दिए हैं?
Nothing. This is a second one, but you can always see on YouTube. There is no problem. Okay, sir. I was not going to discuss any new topic, so that's why I started. You can join. There is no problem. So this is the second question. I think I started with 15th number. I skipped 2 3 questions. Okay. Yesterday we did up to 11, I guess. Okay.
Yes, sir.
So you can very much see the videos. There is no problem. So alpha n inverse is nothing but alpha n and alpha n minus 1, and then because 2 cycles are always self inverse. Okay. So if n is even, it means that this is the product of even number of 2 cycles. So this is going to be even again. So when alpha is even permutation, then its inverse is also going to be an even permutation. Similarly, if we say that alpha is odd, similarly if alpha is odd, okay, so we can then we can write alpha as suppose for example beta 1, beta 2 up to beta m, and beta I are 2 cycles, and m is odd. Okay, because by assumption alpha is odd. Fine. So similarly alpha inverse in this case is also going to be beta m minus 1 ... and beta 2 and beta 1. Fine. So this is the case. So whenever alpha is even, alpha inverse is also going to be even. If alpha is odd, alpha inverse is also going to be an odd permutation. So next question, question number 18. So they are talking about Sn. So in Sn, they are considering alpha. They are considering alpha be an R cycle, beta is S cycle, and gamma is a T cycle. Complete the following statement. So they are talking about the nature of the product, that is alpha beta, and gamma. So in case if alpha is some R cycle, for example, if you're writing alpha 1, alpha, or you can write A, B, C, whatever you feel like, or you can write 1, 2, 3 up to R. Okay, this is R cycle. And then we have beta. Beta is S cycle. Okay, so let us not repeat, or we can repeat also. There is absolutely no problem. Okay, we can write, suppose for example, A1, A2 up to AS, and then we have gamma. Gamma is this is R cycle, this is S cycle, and this is T cycle. So we can write, suppose for example, B1, B2 up to BT. Fine. So they are talking about alpha and beta. So alpha and beta, this is going to be, we can write this like this: 1, 2, 3, and up to R, and then we have A1, A2 up to AS. And note that some of or many of 1, 2, 3 up to R and A1, A2 up to AS maybe same. There is absolutely no problem. Maybe A1 equals to 3, 5 or something. Okay, so there is no problem. I just taken them as a notation. Okay. So they are talking about, they are saying that alpha beta is even if and only if is even if and only if. So they are talking about the condition R on R plus S. So because this is R cycle and this is S cycle, this is R cycle and this is S cycle. So this can be broken as R minus 1, 2 cycles, R minus 1, 2 cycles, and this can be broken as S minus 1, 2 cycles. Are you getting this? Hello?
Yes, sir.
Because for example, if you are writing like this, so you can break it to 1, 3 and 1, 2. Okay, so this was 3 cycle, but you have broken it 3 minus 1, that is equals to 2 cycles. Okay, similarly, if you have 1, 2, 3 and 4, then you can break it like this: 1, 4, and then 1, 3, and then 1, 2. So this is 4 cycle, and you are getting 2 cycles. Okay, so like this, fine. So they are saying that this is even. So it means that R minus 1 plus R minus 2. This should be R minus 1. That is, sorry, S minus 1. So R plus S minus 2. Okay. So if you say that R plus S minus 2. Okay. But they are asking that if and only if R minus, they are telling that this should be even. It means this should be even. Okay, this should be even. So because we are subtracting an even number, so there is it means that if it is even, if and only if this is even. Okay, are you getting? This alpha and beta is even if and only if R plus S minus 2 is even. And this R plus S minus 2 is even if and only if R plus S is even. So this should be even. So here one should write even. Similarly, they are writing this is even if and only if. Okay, for this one there. So similarly, alpha, beta, and gamma. Okay, this is even if and only if, but R plus S plus T minus 3 is even. And this is even when? Because we are subtracting some odd number. So this should be odd. Okay. So this should be odd. I think things are clear to you. Hello.
Yes, sir.
Okay, so let us move to next question. Question number 19. It says that if alpha and beta belongs to Sn, then prove that alpha times beta is even if and only if alpha beta are both even or both odd. I think you can do this. Huh? So for example, if you are taking alpha equals to alpha 1, alpha 2, and alpha n, and then alpha I are 2 cycles, alpha I are 2 cycles. Okay. Similarly, let us take a beta equals to beta 1, beta 2, up to beta m, for example, up to beta m, and beta j are also 2 cycles. 2 cycles. So alpha times beta, they are going to be equals to alpha 1, alpha 2 up to alpha n, and then beta 1, beta 2 up to beta m. So there are m plus n 2 cycles. Okay. So alpha times beta is even if and only if m plus n is even. Okay. And this holds if and the sum of two integers. Sum of two integers, in fact, natural number is even if and only if and only if m and both are even, or m and n both are odd. Fine. So this was this is what we are supposed to prove. Next question, question number 20. It says that associate an even permutation with +1 and an odd permutation with -1, +1 and -1. So they are telling that let us write even as +1. Let us denote in their terms. Let us denote, and odd permutation as -1. So draw an analogy between the result of multiplying two permutations and the result of multiplying their corresponding numbers. Okay, all right. So +1, as we have discussed, that product of two even permutation is even permutation. All right. Product of two even permutation is even permutation. One is even, one is odd. So this is going to be give us odd. Okay. And if both are odd, then we are again going to get even. Fine. So the similar thing is going to happen here. So +1 +1, both are even. So we are going to get +1. It means even. Okay. If we have a minus here +1 and then here and -1, so we are going to get -1. So odd. And if we are going here to get -1 and -1, then we are going to get +1. In this case, this is even permutation. And when we are going to take -1 times +1, so again we are going to -1, and this is odd permutation. So this is the analogy we can draw from multiplication of even and odd permutation in terms of when we are denoting positive one for even permutation and -1 for odd permutations. So next question, it is somewhat easy, in fact very easy. Let sigma be the permutation of letters A through Z that takes each letter to the one directly below it in the display following. Write sigma in cyclic form. I think you can very much write. You can start from A, from extreme left. So you can write A, then A goes to H, and then you can find H goes to M, So A goes to H goes to M, and then you can find M. So you can write M goes to P, okay, and then you can search for P goes to R, and then you can search for R goes to S, and then S you can find somewhere S. Where is S? S is here, okay, S goes to A. So finally we have one cycle here, and then another cycle you can just tick whatever you have already taken. So let us take a B, start with B, and then B goes to D, D goes to G, B goes to D, and D goes to G, and then G to C, and then you can find out C again, C goes to B. Okay, so this is another cycle. You can take E goes to J, and then J goes to L, and L goes to N, and then N goes to F, and then F. Okay, F. Where is F then? F is E. F goes to E. Okay, so this we have 3 cycles until now. Of course, they are going to be only disjoint cycles. So we have F here. No, F I think we have done. So I goes to I is fixed. So you can write or you can skip this. Okay. So what else we are left with? We K, and K goes to O, and O then O mapped to K. Then we have Q. Q to U and U to Q. So this is a 2 cycle. Okay, and then we have T to W, and W to V, and V to T. Okay, so we have this cycle. All right, so and then we have X to Z, and Z to Y, and then Y to X. Okay, so this is a cyclic representation. Okay, both all are disjoint cycles. So can you find the order of this? Suppose this is alpha. Can you guess the order of this? LCM of 2, 3, 4, 5, 6. That is 6, and then we have 4, and then we have 5, and then 1 is there. Okay, 1 is there, and then 2 is there, then 2 is there, then 3 is there, and 3 is there. So that is LCM of 6, 4, 5, 2, and 3. Okay, so you can find it out and write down the answer, the order of this alpha. Question number 22. It says that if alpha and beta are distinct 2 cycles, what is the possibility for alpha and beta? So in case alpha beta are distinct 2 cycles. So for example, you can take 1, 2, and beta is 3, 4. Okay. So what is the possibility of alpha beta? This is going to be 1, 2, and 3, 4. So they are going to they wanted to know what is the order of this one. So alpha beta, order of alpha beta is what? Any guess? Hello. What is the possibility of order of alpha and beta?
2.
2 only. Okay. So only that is we are not telling about the possibility, but we are telling a correct answer. You can note down 1 point for this one. So okay. Next question number 23. Question number 23. It says that if H is a subgroup of Sn, H is a subgroup of Sn, that is they are talking about any subgroup H of Sn, then either every element, every member of H is an even permutation, or exactly half of members are even permutation. So they are telling that, for example, just if you take S3, so in S3 we have A3 as subgroup. So in A3 we have identity because A3 is a collection of all even permutation in S3. Other permutation 1, 2, 3, and we have 1, 3, 2. Okay. Fine. So all you can see even identity is even permutation, and because they are odd cycles, so they are also going to be an even permutations. Okay. So this is the first case. This can be considered as an example in favor of this one. But thing is that we need to prove. So they are telling that then either every member of H is an even permutation. So every member is even permutation, then it means they are talking about in general AN. Okay. So we are done because AN is a subgroup of SN that we know. Okay. But thing is that they are telling that if at all H is going to be a subgroup of SN, and if H has if all member of A3 are not even permutation, then we have half members as even permutation and half members as odd permutation. Okay, exactly half are even or half are odd permutations. Okay, so this is the question. There are two possibilities. So let us see how we can prove this. So in case if H contains all even permutation, then we are done because that subgroup is nothing but AN, and we know that AN is a subgroup. In fact, we can say otherwise that that collection is AN, and AN contains all even permutation is and also is a subgroup of SN. So that we are done in that case. Okay. So let us see the proof. If all members of H are even, then H equals to AN, and we are done because AN contains all even permutation and is also a subgroup of SN. Okay. So now thing is that if H contains at least one even or odd permutation, so we need to discuss these two things. Okay. So let H has at least one odd permutation. I mean to say that there is at least one. There may be so many, but we are considering there is at least one permutation, which is odd in H. Okay, and say it is sigma. That is, sigma is an odd permutation and belongs to H. Fine. Then for each odd permutation, beta in H, sigma times beta is even. All right, because sigma is odd permutation and beta is also an odd permutation. So product of these two is going to give us an odd permutation. Okay. I think we don't have much space here, so just a minute. Hold on, let me. Sometimes. Okay, I'll continue in the next page. Let us see. So we can or so I'm continuing in the next page. Okay. So here I'll continue proof of that. So for each sigma belongs to H, odd permutation sigma, and each odd permutation beta belongs to H, sigma beta is even permutation. Is even permutation. And for each beta, we get distinct sigma beta. Okay. Otherwise, because of cancellation law, we will be getting beta if sigma of beta 1 equals to sigma of beta 2. If they are going to say, then because sigma is same, so and H is given to be a group, then this will be cancelled, and then we have beta 1 equals to beta 2. So this is not possible. So for each distinct beta 1 and beta 2, we are going to get distinct alpha 1 and sigma beta and sigma beta. Okay. So therefore there are at least as many as even permutation as there are odd permutation. So it means I mean to say that at least उतने number even permutation तो होंगे जितने odd permutation है इसमें, ठीक है, क्योंकि हर एक बीटा के लिए आप सिग्मा बीटा डिस्टिंक्ट फाइंड कर रहे हैं और सिग्मा बीटा जो हमारा इवन परमुटेशन है. सो हर एक कोई भी बीटा आई आप उठा रहे हैं ना, तो सिग्मा बीटा आई ये डिस्टिंक्ट आ रहे हैं. तो मान लीजिए जितने भी होंगे तो जितने भी ऑड परमुटेशन है उसके करस्पॉन्डिंग हमें ये मिल रहा है, वो भी डिस्टिंक्ट मिल रहा है. तो एटलीस्ट इतने नंबर तो होंगे ना जितने बीटा आई के हैं. पक्का, कोई दिक्कत नहीं? हेलो
यस सर.
क्लियर है?
यस सर.
ठीक है. सो सिमिलरली we can take beta as even permutation. Okay. So similarly, if beta is or similarly for each even permutation beta in H, sigma, because sigma is fixed, odd permutation, sigma beta is what? Even or odd? Sigma was odd, beta is even, is an odd permutation, and are distinct for distinct betas. Fine. So it means what? In the same fashion, we can say that beta I are odd. Sorry, they are even, and then correspondingly to each beta I, we have sigma beta I, and this is going to be odd. So jitne even permutation hai, so the number of corresponding to each even permutation beta I, we are getting that many number of odd permutations. Okay, so it means what? It means that so there are at least as many as odd permutations are there are even as there are even permutations. फाइन. सो एक जगह हमने प्रूफ किया कि एटलीस्ट उतने नंबर ऑफ इवन परमुटेशन है, एक जगह हम लोगों ने प्रूफ किया उतने नंबर ऑफ ऑड परमुटेशन है एटलीस्ट. फाइन. सो फ्रॉम above we conclude that a number of number of even and odd permutations in latter case. I mean to say that when all permutations are not even. Okay, in latter case are same. Fine. So this proves the result. So next theorem, this theorem, what does it say? Question number 24. H is a subgroup of Sn of odd order. Prove that H is a subgroup of An. Okay. So here we need to prove that H is a subgroup of, but we need to look for some contradiction or something. Okay. Because we are not going to use one step or two step test, something like this. Okay. So since H is a subgroup of Sn and order of H is odd. Fine. Order of H is odd. So every, because you know that so every permutation in H, just by last result, is either even or half even and half odd. Fine. In latter case means when half even and sorry, from here half even or half odd. In latter case if half even and half odd, इसका मतलब क्या है कि नंबर ऑफ एलिमेंट्स को हम दो पार्ट में भाग वो कर पा रहे हैं, ब्रेक कर पा रहे हैं. समझ रहे हो आप? दैट इज इसमें कितने इवन नंबर ऑफ एलिमेंट्स होंगे तभी तो हम पार्ट कर पाएंगे आधे, है ना? समझ रहे हो आप? जैसे A1 A2 अप टू सपोज इसमें एलिमेंट्स में लिख रहा हूँ. Suppose if I'm writing 2021, this is odd number. Can you bifurcate in two parts? No, not exactly. है ना? नहीं कर पाएंगे आप. So it means that number of elements should be even here. समझ रहे हैं आप? है ना?
Yes.
So in latter case, H should be, order of H should be even. So which is a contradiction because order of H is given odd. Fine. So it means that this should be this H of odd order should be some subset of what? Some subset of An, because An contains all even permutation. All right. An contains all even permutations. Okay. And further, H is a subgroup of Sn. H is a subgroup of Sn, and H contained in An. So this H is going to be a subgroup of An. समझ रहे हो आप? H सबग्रुप है किसका? Sn का सबग्रुप है, एंड देन H कंटेंट है किसमें? An में कंटेंट है, तो चाहे प्रॉपरली कंटेंट हो या फिर कंप्लीटली An भी हो सकता है, देयर इज नो प्रॉब्लम. ओके, ठीक है. और H सबग्रुप है ही, तो इसका मतलब कि An का भी ये सबग्रुप होगा, पक्का, कोई दिक्कत नहीं. इट्स ऑल राइट. So next question, question number 25. Give two reasons why the set of odd permutations in Sn is not a subgroup. So anyone?
Yes sir. सर पहला हो जाएगा कि आइडेंटिटी जो होता है वो इवन परमुटेशन होता है, और दूसरा सर कंपोजिशन ऑफ ऑड परमुटेशन जो होता है वो इवन परमुटेशन होता है.
Identity and closure.
Yes sir.
Closure, very good. You can note down 2 points for this. Okay, so we are done with this, and then question number 26. I guess you can do this. This was the solution to question number 23, I think. Okay, this was solution to 23. 26 may, if alpha and beta belongs to Sn, then prove that okay, so this is an even permutation. I guess you can because if alpha is even, then alpha is so there are so many possibilities for this alpha and beta. Okay, alpha beta. So one may be even, this may be even, this may be odd, and this may be both may be even. Fine. So correspondingly, अगर अल्फा इवन है तो अल्फा इनवर्स भी इवन होगा, बीटा इनवर्स भी इवन होगा. ठीक है. सो इस तरीके से करके इन सब का आप वो कर सकते हैं. फाइन. You can do like this. 26th question. You can do like this: alpha and then beta, then alpha inverse and beta inverse, and then you can write alpha inverse, beta inverse, alpha beta. Alpha inverse, beta inverse, alpha and beta. Okay, this you can write like I think alpha beta and then alpha beta inverse. ऐसे भी तो लिख सकते हो, है ना? Hello.
Yes sir.
So this is inverse. ये इनवर्स हो गया इसका, तो ये क्या होगा? आइडेंटिटी होगा ना, है ना?
Yes sir.
तो ये तो ऐसे ही हो जाएगा, ज्यादा कुछ करने की जरूरत नहीं. इवन परमुटेशन हो गया, है ना? तो ज्यादा इसमें करने की जरूरत ही नहीं है. ठीक ना? फाइन. So with this, let us conclude discussion for today.
Thank you for watching this video. To stay updated, please subscribe to our YouTube channel, Cosmos Learning. Happy learning through Cosmos Learning. To watch more, click on any of these cards. Thank you once again.